Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is the DC power supply. Our objective is to learn to use a basic DC power supply and discuss the referencing aspect of a ground connection. Additionally, we'll explore the current limitation feature of a current limited DC power supply. This lecture operates under the presumption the viewers watch the ohm meters and the DC voltmeters lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. For the purposes of today's lecture, we'll be making use of the Tektronix CPS250 triple output power supply. This in no way is meant to be neither an exhaustive review of this tool nor an endorsement of this particular manufacturer or model. I only wish to demonstrate the operation of a representative example of a DC power supply so the viewer can gain some practical exposure to this type of equipment. Admittedly, this is not the most modern nor most sophisticated of power supplies. However, it is rugged and reliable enough to have endured repeated abuse at the hands of generations of first-year electronics students that its sheer durability has made it and others like it a popular choice for numerous electronics instructional programs. A benchtop power supply is an essential element in most lab settings and is used as an adjustable source to supply current to an electrical circuit under inspection. A benchtop power supply takes AC input and converts it to user-adjustable DC power. This is in contrast to a portable DC source like a battery, which converts stored chemical energy into DC electricity. This particular power supply has three outputs, hence the title, Triple Output Power Supply. Two outputs, A and B, are adjustable, and the third is fixed. A single power switch in the upper left-hand corner turns on and off all three outputs simultaneously. We'll explore other features of the power supply like the needle meters, selector switches, and knobs in a moment. For now, we can model the power supply as three independent sources. A and B are variable outputs. Note the variable arrow on the schematic, from 0 to 20 volts DC, and the third output is fixed at 5 volts. Additionally, note the polarity established by each source. The red binding post is positive and the black binding post is negative. The fixed output on the far left-hand side establishes a 5-volt differential between this pair of red and black binding posts. If you recall, we made use of the fixed 5-volt output in the DC voltmeters lecture. A voltmeter measuring the differential between the positive terminal with respect to the negative terminal unsurprisingly demonstrates a roughly 5-volt differential exists between them. As can be expected for a fixed 5-volt source, any pressing, pulling, turning, tapping, diddling, or dorking with any of the numerous knobs, buttons, and switches in the front of the power supply does not, will not, and cannot change the output magnitude by even the smallest amount. Output remains fixed at 5 volts. If we swap the leads such that the voltmeter measured the differential between the negative terminal with respect to the positive terminal, the voltmeter still demonstrates a roughly 5-volt differential exists between them, only that the negative terminal is 5 volts lower than the positive terminal by use of a negative sign. Before exploring other elements of this power supply like the adjustable outputs, let's discuss ground and ground referencing. Ground is schematically symbolized by an upside-down triangle of layered bars. Ground is a major source of confusion for a lot of people, but it needn't be so. Ground is simply a frame of reference. Since humans live on Earth, ground makes a super handy frame of reference because we spend a lot of time standing on the ground. Additionally, a ground connection makes it possible to protect individuals from inadvertent shock and electrocution hazards. We'll discuss certain protection methods involving ground in later lectures and series circuits. For now, let's restrict ourselves solely to discussing the referencing aspects of ground. Let's first consider a fixed 5-volt source in isolation, lacking any reference or connection to ground, forming a closed electrical circuit consisting of a 100 ohm resistor. You'll recall that conventional current travels from the positive terminal of a source to the negative terminal of a source through an electrical load. All meters, all the time, always read conventional current from positive to negative. An application of Ohm's law demonstrates we should expect 50 milliamperes of conventional current to travel clockwise through this system. Electrons, the actual particles that constitute charge movement, in reality move from the negative terminal to the positive terminal. In reality, 50 milliamperes of electrons actually flow counterclockwise through this system. This being said, who cares? It's still 50 milliamperes of charge movement, and an application of the power equation would demonstrate that the 100 ohm resistor would consume 250 milliwatts or a quarter watt of power. Ideally, the inclusion of a ground reference won't change how charges flow through this system. You'll note this power supply has a green binding post on the far left-hand side with a ground symbol on it. This green binding post is directly connected to ground, meaning there is a conductive path between it and the Earth and anything on the Earth. Everything attached to ground has no differential with respect to anything else attached to ground because they're all pooled together at a common point of connection. notably the large sphere upon which we stand, the Earth. We can verify this ground connection with an ohm meter. If this binding post is truly connected to ground, we should observe a very low resistance path between it and anything touching the ground. For example, an ohm meter measuring the resistance from the green binding post to the third terminal on the back of the power supply demonstrates a low resistance conductive path exists between these 2 points. If we insert a plug into the back of the power supply, an ohm meter demonstrates the resistance from the green binding post to the ground terminal on the plug demonstrates a low resistance conductive path exists between these 2 points. If we plug the power supply into an AC outlet, an ohm meter measuring the resistance from the green binding post to a grounded outlet box demonstrates a low resistance conductive path exists between these 2 points. Similarly, an ohm meter measuring the resistance from the green binding post to a metal screw on a grounded metal table demonstrates a low resistance conductive path exists between these 2 points. Note, you may have to scratch some paint on painted metal objects to observe the ground connection. In short, everything grounded is effectively electrically connected to the grounded green binding post. The black and red terminals of each power source in this power supply, however, are isolated from each other and are isolated from ground. No conductive path exists between these 3 sources and ground. Consider the fixed 5-volt source. This fixed 5-volt source has absolutely no connection to ground and is completely isolated from it. Allow me to demonstrate. The DMM in ohm meter mode demonstrates an open or no conductive path exists between the grounded green binding post and the negative terminal. Similarly, the DMM in ohm meter mode demonstrates an open or no conductive path exists between the grounded green binding post and the positive terminal. Both terminals of the fixed 5-volt source are entirely isolated from and have absolutely no connection to ground. Any voltage measurement employing the grounded green binding post is total nonsense and has no meaning whatsoever. For example, this voltmeter measuring the difference between the positive terminal and ground is absolute garbage, because no relationship exists between these binding posts. If, however, we wish to ground reference this fixed 5-volt source, it's a simple matter of electrically connecting the grounded green binding post to one of the terminals. Customarily, one grounds the negative terminal of a source. Here I have included an accessory green wire grounding the negative terminal. The DMM in ohm meter mode demonstrates a low resistance conductive path exists between these 2 points. When we turn on the power supply, a DC voltmeter demonstrates the positive terminal is 5 volts higher than the now ground reference negative terminal. This is exactly the same as we observed earlier. A 5-volt differential still exists between these terminals. Only this time, we have a convenient external reference. Allow me to demonstrate. Given the negative terminal is now electrically connected to the grounded green binding post via the accessory wire, a DC voltmeter similarly demonstrates the positive terminal is 5 volts higher than the grounded green binding post. Given the green binding post is electrically connected to anything else grounded, other valid reference points exist. For example, the positive terminal is 5 volts higher than this metal screw on a grounded workbench. Grounding, in addition to the circuit protection mechanisms we'll explore in later lectures, merely establishes a convenient frame of reference. Let's return to our example electrical circuit consisting of a fixed 5-volt source forming a closed electrical circuit consisting of a 100 ohm resistor, only this time the source's negative terminal is ground referenced. As previously, an application of Ohm's law demonstrates we should expect 50 milliamperes of conventional current to travel clockwise through the system. Electrons, the actual particles that constitute charge movement, in reality move from the negative terminal to the positive terminal. In this capacity, in addition to acting as a convenient voltage reference, ground can act like an infinite source of electrons, which are pulled through the 100 ohm resistive electrical load to the positive terminal. More on this in a moment. As I mentioned previously, customarily the negative terminal of the source is grounded. However, other grounding schemes exist. For example, consider a positively grounded 5-volt source, whereby the positive terminal is directly connected to ground, such that the negative terminal is 5 volts lower than ground. A 5-volt differential still exists, only this time it's from the ground on down. Consider the following voltage measurements and see if you can predict what the voltmeter will measure. Remember, voltage is a 2-point measurement where 1 point's differential is measured with reference to another. First, consider the differential exhibited between the positive terminal and negative terminal with a reference lead of the voltmeter on the negative terminal. Will the ground referencing of the positive terminal in any way, shape, or form affect the differential exhibited between the positive and negative terminals of the source? Second, consider the differential between the positive terminal and the grounded green binding post. Will any differential exist? Finally, consider the differential between the negative terminal and the grounded green binding post with a reference lead of the voltmeter on the grounded green binding post. For the first scenario, the DMM and DC voltmeter mode demonstrates the positive terminal is still 5 volts higher than the negative terminal. This is no different than our earlier observations. A 5 volt differential still exists between these terminals. For the second scenario, the DMM and DC voltmeter mode demonstrates no differential exists between the ground and the positive terminal. It makes sense. They're electrically connected to each other via the accessory wire, and no differential should exist. Finally, for the third scenario, the DMM and DC voltmeter mode demonstrates the negative terminal is 5 volts lower than ground. This is to be expected. A 5 volt differential still exists, only this time it's 5 volts lower than the ground referenced positive terminal. Ground again is merely a handy frame of reference. This being said, most sources, if they necessitate grounding, are customarily grounded on the negative side. Let's again return to our example electrical circuit consisting of a fixed 5 volt source forming a closed electrical circuit consisting of a 100 ohm resistor, only this time the source's positive terminal is ground referenced. As previously, an application of Ohm's law demonstrates we should expect 50 milliamperes of conventional current to travel clockwise through this system. Electrons, the actual particles that constitute charge movement, in reality move from the negative terminal to the positive terminal. In this capacity, in addition to acting as a convenient voltage reference, ground is acting like an infinite sink or endpoint for electrons which emanate from the negative terminal of the source and are pulled through the 100 ohm resistive electrical load. Now that we've examined isolated and both negative and positively grounded sources, let's compare and contrast these last two scenarios. One, a source forming a closed electrical circuit, in which the source's negative terminal is ground referenced, and the other, a source forming a closed electrical circuit, in which the source's positive terminal is ground referenced. In both scenarios, 50 milliamperes of conventional current would travel clockwise, but we know in reality 50 milliamperes of electrons would move counterclockwise. For the negatively grounded circuit, in addition to acting as a convenient voltage reference, ground acts as an infinite source for electrons. In contrast, for the positively grounded circuit, in addition to acting as a convenient voltage reference, ground acts as an infinite sink or endpoint for electrons. Sufficiently massive objects, like the large sphere upon which we regularly circle the sun, can act as both infinite source and infinite sink for all electrical charge movement all the time, remaining electrically neutral. Again, voltage is a 2-point measurement, and voltage measurements inside electrical circuits must use 2 points actually inside the circuit of interest. By employing a ground reference in either form, one simply expands their measurement opportunities. I should note that referencing needn't be limited to the Earth, and other convenient reference points exist, each with their own schematic symbol. For example, consider a chassis ground employed by most automobiles, where the frame and anything touching the frame is considered the reference. Another symbol you may run across is an analog or a digital ground, symbolized by an upside-down empty triangle with an A or a D inside it, whereby some element within a circuit, typically the printed circuit board itself, is used as the reference for two types of signals, digital and analog, used to communicate data. Sufficiently massive objects like the Earth, a car frame, or a printed circuit board in the case of low-power communication signals are large enough to serve as a neutral frame of reference in most cases. Alright, now that I've confused the hell out of you about ground, let's continue to explore the features of this power supply. The Tektronix CPS250 triple output power supply additionally features two adjustable power supplies, A and B, each capable of producing adjustable 0 to 20 volt output. What's nice about these two sources is that they are independently adjustable and isolated from one another and from ground. Importantly, to take advantage of the independent nature of these two adjustable sources, one must ensure that they remain independent by placing the selector switch in the upper right-hand corner to independent mode. The selector switch also allows the user the options of placing the sources in series with one another or in parallel with one another. We'll explore these options in later lectures on series and parallel DC circuits. For now, let's keep the A and B sources in independent mode. Closer inspection of the A and B output terminal pairs lets the user know that the adjustable sources each have an upper limit of 0.5 amps, or 500 milliamperes. Given power as the product of voltage and current, a max of 20 volts times a max of 500 milliamperes demonstrates these two sources also have an upper limit of 10 watts of power each. Changing the voltage output of the adjustable A and B sources is done via the corresponding voltage adjustment knob. The power supply layout makes use of a simple color scheme to identify which knobs control which outputs. You'll note the A source is identified by a gray box. The voltage and current control knobs in the gray box control the gray A source. Here, the A voltage knob is turned a little past halfway. We might expect an output of more than 10 volts, but less than 15 volts. The A current knob is pegged all the way clockwise. This means source A will provide up to the maximum of 500 milliamperes. We'll explore current limitation in a moment. Similarly, you'll note that the source B is identified by a blue box. The voltage and current control knobs in the blue box control the blue B source. It looks like the B voltage knob is turned a little less than halfway. We might expect an output of more than 5 volts, but less than 10 volts. It looks like the B current control knob is also pegged all the way clockwise. This means source B will provide up to the maximum of 500 milliamperes. Again, we'll explore current limitation in a moment. The needle meter on the left displays voltage, whereas the needle meter on the right displays current. The selector switch between the two needle meters can be toggled between the gray A source and the blue B source. Right now, the power supply is set to display the output of source A. When I turn on the power supply, it looks like the voltmeter needle jumps to maybe 12.5-ish volts, midway between 10 and 15 volts. You note the ammeter needle indicates that source A is not providing any current. This is to be expected since no closed electrical circuit exists. How accurate is this needle voltmeter? Not bad, but it's not terribly precise either. At most, the analog scale is used to approximate the output. More accurate voltage measurements can be made with a DMM in DC voltmeter mode. A DC voltmeter demonstrates that source A is actually closer to 13-ish volts. A minor turn on the gray voltage control knob can dial the source A down to 12 volts. When I toggle the selector switch to source B, the voltmeter indicates source B is maybe 5-ish volts. Similarly, you'll note that the ammeter indicates that source B is not providing any current. This is also to be expected since no electrical circuit exists. A DC voltmeter demonstrates that source B is actually closer to 6 volts. A couple turns in the blue voltage knob cranks source B up to a maximum of 20 volts. When we toggle the selector switch back to source A and measure source A's output with the voltmeter demonstrates that source A has remained reasonably close to our previously adjusted value of 12 volts. In short, source A and source B are two independent and independently adjustable sources. Let's make use of the adjustable sources to provide current to a load resistor. Consider source A currently set at 12 volts, forming a closed electrical circuit consisting of a 100 ohm resistor. An application of Ohm's law demonstrates we should expect 120 milliamperes of current. A subsequent application of the power equation demonstrates the resistor will consume 1.44 watts of power. If we were to use a pretty beefy resistor capable of handling 2 watts, we should be just fine. When we build the circuit and turn on the power supply, the analog current scale demonstrates source A seems to be supplying an amount of current reasonably close to our theoretical calculations of 120 milliamperes. You'll again note that the analog ammeter scale isn't terribly precise. We'll explore the DC ammeter function of the DMM in an upcoming lecture that makes possible more accurate measurements of current. Let's do the same with source B, currently set to 20 volts, also forming a closed electrical circuit consisting of a 100 ohm resistor capable of handling up to 2 watts of power. An application of Ohm's law demonstrates that we should expect 200 milliamperes of current. A subsequent application of the power equation demonstrates the resistor will consume 4 watts of power. You'll note that we'll be overloading this particular resistor by twice its rated power of 2 watts. It should handle it, but not for long. We might expect this resistor to heat up and smoke a bit. This should be fun. When we build the circuit and turn on the power supply, the analog current scale demonstrates source B seems to be supplying an amount of current reasonably close to our theoretical calculations of 200 milliamperes of current. The observant among you will note wisps of smoke curling off this resistor, and the pane is rather quickly turning an ugly shade of brown. A thermal imaging camera really tells the truth of how far beyond the power rating we're pushing this particular resistor. Burning electrical components makes a great segue into a discussion on current limitation. This is a current limited power supply, meaning there are hard upper limits of current and power this power supply is capable of delivering, beyond which output will be attenuated or reduced to prevent damage or disaster. This is a great feature for a basic electronics lab where what can go wrong often does on a disturbingly regular basis. You'll note each adjustable voltage source can provide an upper limit of 500 milliamperes of current. This upper current limit is adjustable via the current control knobs for each source. With the current control knobs all the way clockwise, each source could provide the maximum of 500 milliamperes. Halfway, we might expect a maximum of 250 milliamperes. 1/4 turn clockwise, we might expect 125 milliamperes, and so on. As previously, consider source A, currently set at 12 volts, that would ordinarily supply 120 milliamperes of current to a 100 ohm resistor. If we wanted to, we could set an upper limit of 125 milliamperes for this A source by keeping the voltage control knob at 12 volts and dialing the current control knob back to a 1/4 turn clockwise. When we turn on the power supply, everything behaves as we might expect, where 120 milliamperes of current flows through the 100 ohm resistor when it experiences a 12 volt differential. Given 120 milliamperes is below the user adjustable limit of 125 milliamperes, source A provides all 12 volts and all 120 milliamperes of current without a hint of complaint. The user adjusted current limit, however, establishes a hard limit of 125 milliamperes in the event of a mistaken connection or a short circuit. For example, consider a 0 ohm short around the 100 ohm resistor. The 0 ohm short would present no opposition to current flow, and if the source wasn't current limited, theoretically infinite amounts of current would flow through the short. Always a bad idea. However, given we dialed source A's maximum current down to 1/4 of 500 milliamperes, we should expect at maximum roughly 1/4 of 500 milliamperes or 125 milliamperes of current to flow. Allow me to demonstrate. The moment the short circuit is established, current spikes to roughly 125 milliamperes and ceases to increase. Importantly, two events simultaneously occur. One, the overload indicator on source A illuminates, indicating source A is presently hitting the user adjustable upper limit, in this case 125 milliamperes. If this light turns on, either your current setting is too low or something stupid like a short circuit is happening. Short circuits across the terminals of a source present no opposition to current flow and are generally to be avoided at all costs. 2. The current limited power supply recognizes something stupid is happening, in addition to throwing a red flag on the play, takes active steps to avoid a total disaster by reducing voltage. You'll note the voltage necessary to push a maximum of 125 milliamperes of current through an incredibly low resistance short is not our previously established setting of 12 volts, but rather a much, much smaller, essentially 0 volt differential. As soon as we remove the 0 ohm short around the 100 ohm resistor, source A immediately bounces back up to the desired 12 volts and steadily supplies the required 120 milliamperes of current as if nothing unusual has happened, all thanks to the current limitation feature of this power supply. We can use the current limitation feature of the power supply to make sure components don't go up in smoke. Consider a 100 ohm resistor intended for power applications of less than 2 watts. What if we kept source B at 20 volts? However, current limited it to 1/4 of 500 milliamperes or 125 milliamperes by backing the current adjustment knob off to 1/4 turn clockwise. How much power would a 100 ohm resistor dissipate if it was limited to a max of roughly 125 milliamperes of current? An algebraic permutation of the power equation demonstrates that power equals current squared times resistance. Substituting in the upper limit of 125 milliamperes and the resistance value demonstrates that this resistor will dissipate at max roughly 1.6 watts of power. In this occasion, we'll be well under the power rating for this particular 2-watt resistor. Importantly, what magnitude of voltage should push 125 milliamperes of current through a 100 ohm resistor? An application of Ohm's law demonstrates 125 milliamperes flowing through a 100 ohm resistor necessitates only a 12.5 volt differential. Consider source B, currently set at a maximum of 20 volts and a maximum of 500 milliamperes. This is way more than we need on both accounts. If we kept source B's magnitude at the 20 volt maximum, yet dialed the maximum current down to 125 milliamperes, we should anticipate some predictable behavior given this power supply is current limited. Namely, we should observe voltage, currently set at 20 volts, to drop down to only 12.5 volts, such that the maximum permissible amount of 125 milliamperes of current flows through the 100 ohm resistor. And additionally, beyond actively controlling the output voltage, we should see the power supply throw a red flag in the play and indicate that it's in an overload condition by illuminating the overload LED for source B. Let's see if this is the case. As we anticipated, voltage drops from 20 volts to roughly 12.5 volts as current pegs the user-adjustable upper permissible limit of 125 milliamperes. The overload light illuminates, indicating we're pegging the limit. Importantly, given the current limited nature of the power supply, the resistor doesn't go up into smoke this time. Oftentimes, the current limitation feature is used in this fashion to prevent current from exceeding some user predetermined maximum beyond which may damage the components under inspection. The current limited power supply actively reduces output voltage such that current does not exceed this user adjustable maximum. Alright, this is really as far as we can get without introducing the ammeter. We should probably wrap it up. We'll make use of DC power supplies in later lectures. In conclusion, this lecture took a look at a basic DC power supply. We examined operation of a DC power supply and discussed the referencing aspect of a ground connection. Additionally, we discussed the current limitation feature of a current limited DC power supply. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.